Hello everyone. Let me start with a simple question. How do you know that you are moving right now? If you are sitting in a train, you might feel as though you are still. But someone standing on the platform sees you rushing past. So, who is right? The truth is, both are right because motion can only be described when we compare it with something fixed. That fixed system is what we call a frame of reference. Without it, saying the car is moving or the ball is falling has no meaning. Just imagine the passenger in a train at rest with respect to the seat but in motion with respect to the earth outside. That's the magic of frames of reference. So, what exactly is a frame of reference? In physics, it is a coordinate system, usually the x, y, and z axes, that we attach to a fixed point. To fully describe motion, we also need a clock to measure time. Together, the coordinate system and the clock form what we call a spacetime reference system. For example, when we say the position of a particle is given by r of t equals x into I cap plus y into j cap plus z into k cap, we are expressing it with respect to that reference frame. A ball dropped from a height is always measured with respect to Earth's frame, where the ground is fixed. Now, let's classify frames of reference. The first kind is an inertial frame. This is either at rest or moving with constant velocity. In such frames, Newton's laws are valid exactly as they are. The second kind is a non-inertial frame, which accelerates or rotates. Here, Newton's laws don't hold directly unless we introduce fictitious or pseudo forces. For instance, if you stand inside a bus that suddenly accelerates forward, you feel a backward push, but no one actually pushed you. That sensation is a fictitious force because you are observing motion from a non-inertial frame. This is where Newton's first law beautifully defines inertial frames, saying an object continues in its state of rest or uniform motion unless acted upon by an external force. Every frame uses coordinate axes to represent motion mathematically. The position of a particle at any time is given by its position vector. Displacement, velocity, and acceleration are then defined as the derivatives of position with respect to time. In words, velocity equals dr by dt and acceleration equals dv by dt. Suppose a car is moving east along the x-axis. Its velocity and acceleration are always measured relative to that axis. If you look at the diagram, the displacement vector, velocity vector, and acceleration vector are drawn with respect to the same coordinate system. That's how we track motion consistently in physics. But what if two different observers are in different frames? How do they relate their observations? This is where Galilean transformation comes in. Imagine two inertial frames, S and S prime. If S prime moves with constant velocity v along the x-axis relative to S, then the transformations are x prime equals x minus v into t, y prime equals y, z prime equals z, and time t prime equals t. This shows that the laws of mechanics remain unchanged in all inertial frames. This is Galileo's principle of relativity. To picture this, imagine a ball falling vertically in one frame. To another observer moving sideways, the ball appears to follow a diagonal path. Both are correct in their own frames. Let's solve a quick example to see this in action. A train is moving east at 20 meters per second. A passenger walks inside the train at 2 meters per second relative to the train. What will be his velocity with respect to the ground? Case 1. If he walks in the same direction as the train, velocity relative to ground equals velocity of person relative to train plus velocity of train relative to ground. That is 2 plus 20, giving 22 meters per second east. Case 2. If he walks opposite to the train's motion, then it becomes minus 2 plus 20, giving 18 meters per second east. This is the principle of relative velocity. The actual motion of an object depends on the observer's frame. If you look at the diagram, arrows show the train's velocity, the person's velocity, and the combined velocity seen by someone standing outside. So let's quickly recap what we've learned today. Motion can only be defined with respect to a frame of reference, a chosen coordinate system and clock. Inertial frames obey Newton's laws directly, while non-inertial frames demand the introduction of fictitious forces. The Galilean transformation helps us shift between inertial frames, ensuring that the laws of mechanics stay the same. And through relative velocity, we saw how the same event can appear differently to different observers. This understanding of frames of reference forms the foundation of modern physics, from the motion of cars and trains to the deeper ideas of relativity and dynamics. I hope this session helped you build a strong intuition about frames of reference. See you in the next lesson, where we'll dive deeper into the world of motion in physics.